Hi, everybody. While we're waiting for those who may come a couple of minutes late, let me mention a couple of things. One is, since we have finished the subject of system identification, there is a homework problem set which deals with that. So it would be a good idea to do that homework along with all the problems we have in the lecture notes. It's a pretty good collection of material so you can get a hands-on experience and feel for how these systems may behave when you have data of a certain kind, excitation of a certain kind, experiments, and so forth. Number one. Number two, as I mentioned earlier in the semester, I've been working with a company to get a demo of their industrial software that is used essentially in all chemical plants and refineries in particular. So we can see a demonstration of a real industrial system in applications and make the connection with what we are learning in theory. So these were administrative details, and let me share my screen so we can start our discussion. So we are going to start our last and perhaps most exciting subject of this course, which is multivariable control systems. This is in a new PDF, multivariable control, which describes the material. Before we do anything, a few things about what all this business is about. So all chemical processes, practically all chemical processes, are multivariable in nature. Namely, when we control things in a chemical plant, it's not just one thing that we control. It's usually multiple things. And naturally, systems that control chemical plants are multivariable control systems. Now, we started with single loop systems, how a single feedback loop behaves, because that's a good module to have a good grasp of, because to build good multivariable control systems, we need to understand first how a single input, single output control system behaves, so we can see how those systems, the multivariable control systems behave. Let me try to give this, to explain this by an example. So we'll take our favorite distillation column, a system that is studied extensively, has been studied extensively, and it is now mature as far as control goes. So we have the reboiler and the condenser. So we have a vapor flow rate, a liquid flow rate. There may be a control valve here. There may be a control valve here. And typically we may connect the purity of this stream to the vapor flow rate, and maybe the purity of that stream here at the top with that flow rate, the liquid flow rate. And there may be other things of interest. Here, for example, you may have level controls. This may have a level controller here by having a control valve that opens and closes there. So the main idea again is that there are typically multiple variables in all of these systems. And when we build feedback loops around those systems, essentially we say let's look at each one of these loops. So let's look at this and at this and at this. And maybe those do not interact very much. Maybe they interact a lot. So let's see if by designing each one of these loops individually, we can create an overall structure which will work well even if there are interactions, which immediately makes the case for the 5 questions that we already posed for the design of control systems. It was, what are our goals? What are the measurements? The measurements and the manipulations. What are the interconnections? And finally, what is the control law? The goals for a single input, single output loop may be simple. Just keep y close to set point. But when you have multiple loops, you may have other goals. Here, for example, it could be all of the y's to be at their y set points, and those now on the right-hand side may be interpreted as vectors. But you may have other things which may also be in single loops, but they are more prevalent in multiple loops. For example, you may have that y must be between max and min. Example, in a distillation column, you may want this purity not to be below a certain value because you won't be able to sell your product, and not to be above a certain value because you know from experience that you're wasting money if you produce too pure a product. Okay, these are some typical considerations that you have when you go to the goals of your control system. So you may have objectives and constraints. What can be controlled and what can be manipulated? Well, it's not always so simple. If you just have this room and the temperature of this room, you just measure the temperature of this room to have comfortable environment. But if you have a column, well, do you measure this purity here and manipulate this, or do you manipulate that, for example? Okay, that's one way to do it. And down here, same story. How do you manipulate? What do you manipulate? What do you measure? So these two are very important. And then when it comes to how you design loops, well, if you have a single input, single output system, this is trivial, but here you may have issues. Namely, do you consider many single input, single output loops? Do you consider one multiple input, multiple output big controller? So let me draw this. So would you take all of these measurements, this measurement here, this measurement here, this measurement here, take them to a controller so that it is a computer essentially, that would generate commands and would send these commands to the corresponding variables. So that would be here, and that would be. So do you do it like that, or something in between? So is your controller, if you want to create the structure here, is your controller essentially a diagonal controller, 3 single input, single output controllers, or could it be one single input, single output, and a 2x2, or could it be a 3x3 controller? Or so which is it? Okay. There are good tools to assess this quantitatively, interestingly enough, and it's a combination of process knowledge and a little bit of math. Thankfully, the math is easy. It's not difficult for how this is done to tell the structure of the system. We'll see aspects of this as we go along in this very last chapter. Finally, because many control systems are here or are now of this configuration. Let me put it here. Well, I'll just do it. Namely, there is a computer rather, which takes multiple measurements and sends multiple manipulations simultaneously. The idea is, how does this work? What's inside this? Okay, what is this C? How does it do all that? Typically, this controller will determine these flow rates that will have to be delivered here. Of course, we have seen this a number of times for cascade and feed-forward control. We'll see these things in a bit more detail, actually, but I wanted to start the discussion now. So essentially, this computer may send a command directly to this control valve here, or this may be cascaded. Namely, you may have here the control valve. You measure the flow rate. You have a flow controller. And the measurement that comes from above is essentially the set point to this controller. So this is called cascade control. We'll spend a little bit of time more specifically, but it's a standard control scheme that is used extensively. So all of these flow control loops are cascaded to this system, for which typically there is the name model predictive control, or MPC, which is now the de facto standard of advanced control in practically every industry. It started in the refining and chemicals industry in the late 70s, because those are slow processes. Now computers are so fast, you can do it for very fast processes also, for anti-lock brakes, for jet plane control, for engine control, for all kinds of things. Model predictive control is a very successful strategy that can deliver very high performance control with multiple objectives. More about that as we go along. It is worth mentioning, actually, the overall hierarchy of what I just mentioned here in terms of this example. So let me borrow once more my the figure that I have from in the lecture notes, which is worth discussing on one more time. So second. It's this first figure in the introduction that I want to focus on here, which we discussed already earlier on, but it's worth discussing it again because it's at the essence of how most refineries, practically all refineries and chemical plants, are being controlled today. So let's discuss this one more time. So I use the distillation column example to explain what is shown here. And I notice again, I forgot to put these arrows here, pointing these. I'll add these in the notes. So I deliberately kept this old figure, which shows PC technology of vintage 90s or 80s, I would say. My intent was to show that in the 80s, there was already technology that allowed people to do this quite well. this real-time optimization at multiple levels. So let's see again what's going on here. At the bottom here, you have the chemical plant. Okay, so this is the process. Right above it, and you see these arrows which take a measurement and they send a command. So this is a sensor. This is a Coriolis sensor, for example. This is a sophisticated valve. This is another sensor, flow sensor, another pressure sensor, a valve, another sensor here for flow, integrated sensor and valve, and all that. I deliberately kept all of these there as an indication for hardware sensors and actuators. And those are PID controllers, essentially that deliver flow rates for the most part, maybe pressure, but mostly flow rates. What are the set points of these is dictated by model predictive control. And you may notice already that these lowest level controllers work in a time scale of, say, seconds. They take measurements every second, boom, 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 or split second, actually. Boom, 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 every second. The model predictive controller sends commands every 1, 2, 3 minutes, practically speaking, for chemical plants. There's nothing magic about it. It's just that the time constants and what is observed there are such that seconds for PIDs, minutes for MPC work well. In other systems like anti-lock brakes, the sampling period is much shorter. You have hertz, or so you may have 10 hertz sampling frequency, or even higher, 15, 20. That's very common in cars, and that's why when you slam on the brakes, you hear this abrupt going on, which is your pump actually taking a measurement and pumping the brakes at that frequency, which is quite high, and it prevents the car from skidding. It's the same technology buried there under your car. Continuing on chemical plants, the model predictive control system, which will dictate flow rates and maybe pressures, but mostly flow rates at the bottom, needs to be told what kinds of, needs to decide rather, what kinds of flow rates it should dictate. And this is determined by the real-time optimization system, which tells the MPC system what to produce, what concentrations it needs to have, at what temperatures, have reaction rates desired, heat transfer rates desired, and so forth. These levels may not be so distinct these days. There may be a meshing and combination of these levels. For example, the industrial package you're going to see a demonstration of in a few lectures actually blends real-time optimization and control. It solves a linear programming problem. We'll see this in detail in a couple of lectures. And regulation in real time. And real-time optimization uses a non-linear simulator to optimize over the next shift, let's say, in a period of hours. So you see the time scale becomes longer and longer and longer. Planning and scheduling, we don't look at this very much in this course, but that's why in your MCHE courses, there is a course on linear optimization, which is offered by a number of departments, such as industrial engineering, electrical engineering, mechanical, and so forth, or in the business school, which is optimization over even longer time scales. And there is structure in these problems, which is why people look at these separately from other problems. So this is a discussion that we had before, and it's worth repeating it again, which is why we did that. Now, to work with multivariable control systems, we need, again, some mathematical tools and machinery, which is what we have done for everything that we have covered so far. So section 2 in the notes covers all that. As I have said repeatedly, I'll have to apologize in advance. This is a somewhat dry section. We have seen some of that before, so I'll go over this once more relatively quickly so we can feel comfortable. So section 2 says in section 2.1, time domain representation. So if you have, say, a column, you may have differential equations that look at the compositions, say in the liquid or in the vapor, as a function of time at each tray, and there are these differential equations that describe these. Or if you have a reactor, you may have a time derivative for the concentration of a reactant and a time derivative for the temperature in the reactor. So this is again for distillation column. This is for a reactor. For any system that you may look at, you may have these equations, and associated with these, you may have equations that focus on the outputs of the system. For example, you may want to look at the top purity, which is the, let's say, if you take the condenser as another state, this is the n+1 state of your system. And if you want the reboiler, xb is x0 of t, so you may consider the states. Same thing with the reactor. For the reactor, it may be that the first output is simply the concentration, the second output may be just the temperature, or there could be other options. For example, you may have, here's an input, the flow rate to the system, so it could be flow rate multiplied by concentration. That could be another output of your system, maybe in addition to these outputs. So maybe you want to add this. In general, those are called the state equations, and they are ODEs. And these are called the output equations. They are algebraic equations. So what are the states of the system? The states of the system are all of these variables whose derivatives, first order derivatives, appear on the left-hand side of these ODEs. And these are called the states of the system. And the name for such a representation of a system is a state space representation. So this is a state space model. In general, a state space model is of the form x dot of t or x prime of t or dx over dt, and those are vector, 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 is a function of the state of the system and the inputs to the system. Those inputs can be manipulated, can be disturbances, can be a combination of the two, everything that is an input to your system. So this is the input, this is the state. And we have said it repeatedly, so let me do it write it one more time, that x is a vector, and x of t is a vector x1 of t all the way through x, let's say, n of t. Okay. Same thing for the function f, which has components f1 through fn. Same thing for u of t, which is an input, which has u1 of t, um of t. It has all of these components. And you can do the same thing for the output. Y of t is going to be y1 of t all the way through yq of t. You can use these. This is the representation of your system. At steady state, you have obviously the differential equations. Oh, I forgot to write the output equation. So y of t is h of x of t u of t. So this is the state equation in vector form, and this is the output equation in vector form. State output. At steady state, obviously, this quantity here is equal to 0. So we have 0 is equal to f x at steady state, u at steady state, and y at steady state. That vector is equal to h, that vector valued function, x at steady state, u at steady state. Okay, and those are all algebraic equations. Incidentally, this equation here does not have to be square, nor does this one have to be square. There may be no square equation, so the input u may not be defined uniquely, but this equation will always be satisfied at steady state, right? We may have more inputs than outputs at our disposal, so that may be the situation. And if we want to find what is the steady state, we'll have, given the input here, we'll have that the dimension of f will be equal to the dimension of x. So this defines the state of the system, the steady state for the states of the system, given the inputs of the system. We'll do examples in a second, actually, to visualize this a little better. Continuing on this, we said that if we have a multivariable system operating around a steady state and we want to control it, linear control theory is pretty good because the controller will keep the system near the steady state, hopefully. So linear theory is pretty good. It works, has been working very well for a very long time. And in practice, it's a very useful tool. So you can take an approximate linearization around a steady state, which says that if you have x prime of t is equal to f of x of t u of t, then this right-hand side is approximately equal to f at steady state plus the Jacobian of f with respect to x at steady state times x of t minus x of s plus the Jacobian of f with respect to u at steady state times the deviation of u from steady state. We have called these deviation variables. And it's trivial to understand that this derivative is equal to that derivative because at steady state we have a constant. So you have now an approximate linear model that connects this with that plus that. And we typically call this matrix here A, this matrix B. So this can be written in a compact form. Delta x prime of t is A delta x of t plus B delta u of t. And most of the time, these deltas are removed because it's a lot simpler to just write the state space system in this form with the implicit understanding that everything is in deviation form. Okay. This equation, the x prime equals ax plus bu, is, according to some statistics, the most widely studied equation in the history of engineering. It competes with Navier-Stokes for fluid mechanics. Navier-Stokes is more difficult because it's very nonlinear with turbulence and all that. This is not easy either, but nonetheless, this became extremely popular in the 50s and 60s with the space program and aerospace control, and then with electronics and microelectronics and with servo mechanisms and everything else. It became the workhorse of a huge body of literature and technology, and to this day it remains a standard equation that appears in countless publications. X dot equals ax plus bu, and the companion equation to that, as you might guess, is the output equation, which says that y of t is approximately equal to y at steady state plus Jacobian of x with respect to h with respect to x at steady state plus Jacobian of h with respect to u at steady state times the deviation, and this is delta x t, and this is delta u of t. So this is equivalent to y of t is c delta y, if I put y of s to the left, c delta x of t plus d delta u of t, where this is c and this is d, and typically we drop these, sorry, the deltas, so we have y of t is cx of t plus d u of t, and I'll frame this as well, and I highlight them because this is, again, a classic representation of multivariable systems, which captures the dynamics and the output, so it captures the complete input-output behavior of these systems. Sometimes people don't write these equations, they just put the A, B, C, D. That's a semi-standard notation to indicate that you basically know the matrix A, B, C, D. And the reason why people don't bother to write all the equations explicitly is because you can go back and forth with from the time domain to the Laplace domain and back. Namely, from these equations, you can immediately get the corresponding transfer function that connects the input to the process, u in the Laplace domain, with the output of the process. And it takes just one line to do the math. You take Laplace transforms of this, and then you use the output, and eventually you get y of s is a transfer matrix, which is C si minus a inverse b plus d. So give me A, B, C, D, I'll give you the transfer matrix. And it turns out you can do the reverse also, which is a bit more difficult, but nonetheless, that's a topic for another more advanced course. Suffice it to say that there is software that can help you do that. If you just did your step response experiment and you want to get a state space system from your transfer matrix, the software will do it for you. Okay, MATLAB has it in the control toolbox. It's not difficult. So from this, let me mention quickly, and we've done some of that already. So you have this matrix G of S equals G11 of S, G12 of S, Gn1 of S, Gn of S. So this is my transfer matrix. And for this, I can define the poles and the zeros. The poles are easy in the sense that you take the individual poles, and those are essential. These constitute the poles of the transfer matrix. So take each one of these transfer functions, find the poles. Those are the poles of the transfer matrix. The zeros are not the individual zeros, and I'll explain shortly why that is. Those are not the individual zeros. Rather, the zeros are the values of S such that, well, let's say S equals Z, such that the determinant of G of Z is equal to 0. That's how the zeros are defined. And we'll explain why. And the explanation is in theorem 2 of the nodes on page 6 that connects time and Laplace domains, and we'll see this idea in a number of times. So a basic theorem, which is fundamental and very simple, is that poles of G of S are in the eigenvalues of the matrix A. So that's a theorem. Why is that? Well, this is a transfer function G of S, right? G of S is C SI minus A inverse B plus D. All right, now the only place where S appears is in this and inverse, and there is a nice theorem from matrix algebra, which you may not remember, but that's okay. I'll remind you that theorem. It says that the inverse of a matrix is the adjoint or adjugate. There are many names for this matrix M. Over the determinant of this matrix M. So if this matrix M is this here, SI minus A, that means that this transfer matrix is C, the adjugate of SI minus A, over the determinant of SI minus A, B, D. Well, that then says the following. The poles of G of S will appear because of the denominators here in these fractions, right? That's standard, because that's the only thing that is in the denominator. Everything else is just numbers in the numerator. Good. So the poles of G of S are the points of S, the values of S, where the determinant of SI minus A becomes 0. Oh, but these numbers S, what do we call them? What do we call these numbers S where the determinant of SI minus A becomes equal to 0? We call those the eigenvalues of A. That's by definition what we call eigenvalues. So that's it. That it takes half a line to prove that theorem, which is the equivalence between Laplace representation, Laplace domain representation, and time domain, state space representation. So the theorem again is that the poles of G of S are the eigenvalues of A, which is why people talk about those things without any serious distinction. When you say the poles of a system, it could be either the eigenvalues of A or the real poles of G of S and vice versa. You may say the eigenvalues of G of S and you mean the poles of G of S, so you mean the corresponding eigenvalues of the matrix A in the system. And people go back and forth very easily. Now, you can go from such a state space system in the time domain in continuous time to a state space system in discrete time. Let's see how. So we learned that state space system, I'm dropping the delta now, it's just A, B, C, D. Is C plus D. Well, for such a system, which is in continuous time, you can find the corresponding discrete time. Well, one simple way would be to say this is xk plus 1 minus xk over delta t approximately equal a xk plus b uk, which means that approximately you have xk plus 1 is about I plus delta t a xk plus delta t b uk. And sometimes this is called a matrix gamma, and this is called a matrix phi, and this is an approximate representation of my system in discrete time for the state equations. And the output equations are trivial. This was for the input. The output equations are trivial because they're algebraic. So you just have yk exactly equal to cxk plus d. Okay, it's these that are the important ones that capture the dynamics of the system. And again, this is approximate. There is also an exact representation of my equations. So instead of having it like this, you can have xk plus 1 exactly equal as opposed to approximately equal. And now you can have, well, let's call those the approximate ones. So phi plus gamma, okay, where this phi here capital is defined as e to the at. T is the sampling, t capital is the sampling period, and gamma is defined as the integral from 0 to t e to the a r dr multiplied by b. These are good to know. It's unlikely you'll ever do this by hand, although it would be instructional doing this by hand. In fact, we have learned what this is, e to the at. E to the at can be defined in general. E to the t is defined as p e to the lambda t, p inverse, where lambda is a diagonal matrix that has the eigenvalues of your matrix A, and P is a matrix that has the eigenvectors of this matrix, Vn. And of course, this is P inverse. It has the right eigenvectors, Wn transpose, and you have, of course, that V1, Vn times W1 transpose. I should reverse it actually. Reverse it. So you have W1 transpose, Wn transpose, V1, Vn. This is P inverse, this is P. So by definition, the product P inverse times P must be equal to 1. 1, yes, the identity. 0, 0, which means if I multiply, let's say, this by that, I must get the 1. And if I multiply the second one by 1, I must get a 0 and 0 and so forth. Standard matrix algebra. So all that, why do I mention all this? This you don't need to go through in terrible scrutiny unless you ever have to use it. Okay, so the important thing is to know that there are specific formulas that make this xk plus 1 exactly equal as opposed to approximately equal to the continuous time system. So if you drive a continuous time system by a computer and UK changes at every sampling time, this is an exact representation of my system. And of course, for the discrete time system, you can also find the corresponding transfer matrix. This is exact same dynamics, exact same mechanics. So if you want to get G of Z, it's the same story. It's gamma Zi minus I inverse, sorry, C times gamma plus D. This is the transfer matrix in the Z domain. You can go back and forth, and there is plenty of formulas here, so I don't want to bore you with all that. Rather, let's do an example so you can see this. Example 1. It's a chemical reactor. We've seen this chemical reactor several times. Example 1 is on page 7 of the notes. So I'm going to copy a few things from the notes because they are worth making specific so that we won't use hand waving to explain those things. So this is a reactor. We've seen this several times. So it's continuous flow. There is an exothermic reaction. There is a cooling jacket here where coolant flows through. These are the two equations that I get from a mass balance and an energy balance. The volume of the liquid is assumed to be constant because you can manipulate the flow rates very quickly to keep them equal. So I'll just use these two equations as my two basic equations to describe the dynamics of my system. So let me put them in my notes so that I can work with them and see what's going on here. Okay, so these are my equations. So let's do it together. So we have here, oops, we have here the states. Well, actually, yes. So we have this vector CA and T. What did we say we call this vector? Yeah, the state of the system. Inputs to that system may be, let me use another color, F, the flow rate, the coolant temperature, that would be another input. So here I'm going to put these as the inputs to the system. So F and TC. So these are inputs. Notice that I didn't include any specific disturbances here. It could be, for example, that I might consider as a function of time this Ti here, which could be a disturbance. This could be another disturbance here. If those were left to be functions of time, the model will still be okay. Those could be two disturbances. There could be other disturbances in the system. So I'll leave that for another consideration. Now, outputs to the system. In the notes, I say that the two outputs are trivial. The first output is, well, let's put them here, is CA equal to the first state. The second output is temperature. I could have a different set of outputs. I could have the concentration, the temperature, and the flow rate times the concentration in that, okay? Or I could have another set of outputs. I could have CA. I could have CAI minus CA to see how much of A was consumed, T, and F, CAI minus CA. I could have any of these. Right? The algebraic equations that I can consider for the outputs can be anything I can think of. Now, for this system, I gave it some specific values and I found a steady state. I don't want to spend time doing the algebra, so I'll just copy everything from the notes again, and I'll just move on. So I can solve these equations and at steady, the above equations at steady state. So if the inputs to this system are these values, so we said the inputs are here, F and T. So if these inputs are at these values, it won't let me Okay, it doesn't let me highlight it, that's fine. So let's just do that. So if you have these values, then you get these two values for the state, which are values for the output, and this is your steady state. Fine. What do you do after that? You can linearize your system around the steady state. So how does linearization work? Well, this first equation is F1 of the states, which are CA and T, and the inputs, which are F and TC. So these are states, X of T. These are inputs, U, T. And this is F2, same story, CA of T, T of T, F of T, TC of T, states, inputs. So linearization has to proceed by taking F1 and F2 and taking the derivatives of these. So let me do it here so we can keep track of what's going on. So the matrix A is going to be partial of F1 with respect to the first state, which is CA of T, partial of F1 with respect to the second state, T, partial of F2 to CA, partial of F2 with respect to temperature. All this at steady state. And if I do the partials, well, let's go here. This is this. So what is the partial of this expression with respect to CA? Let me highlight it. The states. So this is CA, CA, T, CA, T, T. Let me highlight the inputs as well. So F, anything else? No. Okay, so let's do take the derivatives together. So the partial of F1 with respect to CA is here, right? Yes, so it's negative F over V, and it's F at steady state, where V and this expression here, partial with respect to CA, so it's minus K0 e to the minus E over RTS, because everything is at steady state. That's the first element. Then we have to take partial of F1 with respect to T. Okay, T is here. It's the only place where I have T, right? So I have to go with the exponential, and you know how to take derivatives of these expressions. So first of all, this and that come out as a constant. So you have K0 CA at steady state, correct? And then I have the derivative of e to the something. It's e to the same something multiplied by the derivative of the something, correct? The derivative of the something is going to be minus e over r. And then its derivative of 1 over t. The derivative of that is t squared, right? T to the minus 1, derivative of that is to the minus 2. Square is, and there's one more minus, so minus. Okay, just standard derivation, nothing special. Second expression here, taking derivative again with respect to CA, so that's easy. That's the only place where you have CA, so you have J, K0e to the minus E over RTS. And the last one, what is the last one? Partial of F2 with respect to T, where is T here? This is one T and this is another T. So I forgot to highlight it. Okay. So the first one gives you, so let me put this here. So the first one gives you what here? You have minus Fs over V. And the second one has this whole thing here. And there is an extra J, right? So it's minus J, and this is from above. Yes? Plugging in the numbers, so I'm not going to do it in real time. I just did it. I did this with software, obviously. Okay, I didn't do this by hand. I've done it by hand. I did it 40 years ago. I'm not going to do this again. So this is going to give me minus 16.97 minus 177.3 0.4479 2.027. As I have repeatedly said, there is nothing magic about 4 significant digits. I do not even suggest that I know these numbers with 4 significant digits. It's just a way to carry enough detail forward so we can keep track of what's going on. In fact, we have said repeatedly that for all intermediate calculations, you keep all the significant digits that you can carry in your computer. The final result is with as many digits as it makes sense. So this is a same story for B, and I'm not going to redo this again, so I'm just going to show the results from the note. So 5599 0 minus 128.2 2.059. The matrix C is very easy because it's diagonal with 1, 1. Each state is a corresponding output. And the matrix D is also very easy because it's 0, 0, 0, 0. No direct effect of the input on the output. Okay, good. And what do we do with this? We can do a number of things. For example, we could design controllers directly in the time domain. A method that we're going to see is the linear quadratic regulator. The linear quadratic regulator, what is this name, first of all? It's called linear because the model is linear. Quadratic, but because there is a quadratic objective, it's a quadratic control objective. Essentially, it means to minimize, to make the sum of squared errors or the integral square error as small as possible when you start from a certain initial condition. So this is a linear model. And regulator, because it deals with the regulation problem, meaning if you start from a state that is not the steady state where you want it to be at 0, and this is one state or one output. How can you bring this down in the best possible way? Okay, that's the linear quadratic regulator. Associated with that is a corresponding cost, which is the cost of x of t squared plus the cost of the input that you use squared dt 0 to infinity. You have as much time as you need. And frequently there are weights on these Q and R, and because these are usually vectors, you have x transpose of t q x transpose, where this is vector matrix vector, plus u transpose t r u, integral 0 to infinity dt, the whole thing. This is the linear quadratic regulator. The linear quadratic regulator starts with A, B, C, D, with this you get a controller. It turns out, and we'll see this again, but I mentioned it very easy. It turns out that for this problem, the optimal solution is actually very simple. And it's the following. It says that the optimal input, the input that makes this cost minimum, is actually a constant times the state. So you can infer that if I am at x0 here, this is the value x0, the optimal input to use is a linear function of the state where I am. This is a famous result. And this gain actually can be calculated by a famous equation called the algebraic Riccati equation, which is a matrix equation. That's another equation that has been studied to the umpteenth degree, and we know pretty much all its secrets, how to get it solved and all that with software. And we'll come back to this when we deal with MPC. But I mentioned it early because there is a connection with state space representations. A state space representation, if I know the A, B, C, D, is a natural description of my system, so I can get the linear quadratic regulator for that system. In fact, what MPC added to this whole picture is constraints. It solves this problem subject to constraints on input. Let's say this is between a minimum and a maximum value, and the outputs are also between a maximum and a minimum value. In fact, the constraints can be a lot more interesting, not just these simple bound constraints. This simple blue set of inequalities created an entire new technology in the late 70s, which has become, like I said, the de facto standard of advanced process control. It was very difficult. It took a couple of decades to figure out how this system behaves, how to ensure stability to start with, and good performance and robustness and all that. But all that is now mature. We know how the systems behave. They are fairly elaborate and complicated, but you understand them and they work very well. More about that on MPC. But let's continue here on something simpler. Okay, so in this example, we took, where are we here? Let's go one more time from, let's recap where we are. So we are doing this example. It's example 1 in the notes. What is this example about? We have a reactor. We develop these equations. How? From first principles. Mass balance, energy balance. Accumulation equals in minus out, did all that, boom, 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 boom. Eventually, we got there. If you want to see how this is done, by the way, an excellent source for that is Stephanopoulos, the 84 edition of his textbook. It's an outstanding description of how this is done right. So you get these. Okay, so what do we want to do with these? We want to linearize them around a steady state. Why steady state? Because this describes a continuous flow reactor, which is supposed to work at steady state. We want to control it at that steady state. So at a steady state, we want an approximate linear model. Why? Because for linear models, we can apply good theory, design good controllers, we have good tools, and it works quite well. So we apply our theory. What theory? How to go from this model to an approximate linear model, and then transfer functions and eventually controllers. So we are here where we have linearized our system. We get the linearized version. So we have the A, B, C, D matrix of the linearized version. I took a quick deviation from our main discussion to explain that ABCD can be used directly to get a controller that's called the LQR, the linear quadratic regulator, which can be used quite well. The linear quadratic regulator relies, of course, on state feedback. You must be able to measure all the states of your system. Here in this case, if you measure concentration and temperature, easy, so you do use state feedback to control your system, fairly simple. With that, we we'll continue to the final step of this exercise, which is to get a transfer matrix and then see poles and zeros. So the transfer matrix of this is by the formula. I'll write it again. C SI minus A inverse B plus D. Well, you plug A, B, C, D from up there. We covered these A, B, C, D. You plug them into this expression. You do the math. Actually, MATLAB will do that for you. And I have this in the homework that you're doing. The very last homework set, it has examples that show you how to do this, how to get transfer function from state space and vice versa. And there are solved problems in the notes, both in the notes and in the appendices of the notes. It's fairly easy to do this. You can do it, of course, by hand, and it's always a good idea to do it once by hand and just see what this involves. Well, don't try A with everything, just try A to B, A11, A12, A21, A22. That's easy. Okay, plug, and then B is B11, B21, and C is, oh no, I forget. It's B11, B12, B21, B22, and C is now, C is easy. It's 1, 0, 0, 1, so D is easy, 0, 0, 0, 0. Okay, so it's fairly easy. It can be done by hand in 5 minutes. It's not a big deal. It's fairly easy. The result you're going to get is lengthy, so I'll copy from the notes so we can save some time. And again, I mentioned the result with many significant digits only to suggest that in intermediate calculations, it's a good idea to carry all of these. Otherwise, you may get weird results. So this is the result. So we got finally the transfer matrix that we were looking for. You have here these transfer functions G11, G12, G21, G22. So that says the outputs of the system, C A of S, T of S, are related to the inputs in deviation form as always. So delta, delta, delta F, delta TC of S of S in the Laplace domain, like this. Before we go forward into section 2.4 that discusses again multivariable poles and zeros, a couple of quick observations. The effect of delta F, the feed flow rate, on temperature has this form here. So this form has these poles, the roots of this denominator, and you observe that the denominators of all 4 transfer functions are the same, correct? Yes? Why are the denominators of these transfer functions the same? Because this inverse is, as we said, the adjugate or adjoint of A divided by the determinant of SI minus A. If you take the determinant of SI minus A, you're going to get these denominator, the same denominator for all 4 of them. Now, in some systems, you may have pole zero cancellation. In some terms, one of the zeros here there is a 0 in the numerator. So it could be that one of these terms might be equal to 1 in the denominator. So you may end up having first order transfer function individually. But in general, all 4 of these denominators are the same. Okay, so that's one observation. What can you observe about the numerators of these 4 transfer functions? Just an obvious observation. What kind of polynomials are they that we put it like this?
Second order.
First order, all 3 except this one, which doesn't have a numerator, right? So this doesn't have any zeros. These all three have zeros there. Okay, so that says something about the dynamics of the system. Let's look at the individual zeros here. This has a zero, which is the root of the numerator, which is positive or negative. Negative, good. This is negative, this is positive, right? So what does that say about the effect of this Laplace transform or this variable on this output? These two are related by this transfer function. Okay, so let me write these more explicitly. So this is delta CA, delta T in the S domain is G11 of S, G12 of S, G21 of S, G22 of S, delta F of S, delta TC of S. And if I want to expand all this, I have delta CA is equal G11 delta F plus G12 delta TC, and delta T is equal G21 delta F plus G22 delta TC. So that transfer function G21 here, which is this one again, which connects this to that. So I'm highlighting everything. That transfer function has a zero, which is positive. It's in the right half plane, right half of the complex plane. It's real, of course. This is real and imaginary. This zero is here somewhere. It's at 332.5 divided by 128.1. Okay, it's here. Because this transfer function has a right half plane zero, we know that it has what we call inverse response, namely, if we change delta F here, so delta F, the output delta T is going to evolve how? Eventually, where it's going to go? It's going to go to where this transfer function is when S is equal to 0. So it's going to go to 332 point something or 44 point something. So it's going to go eventually to 332.5 divided by 44.97. Okay. This is the steady state gain. So if we make a unit step change, eventually this is going to go to this value. If we make a change of size m, it's going to go to the gain times m. Okay, that's the final value, positive. But how is it going to go there? Yes, first it's going to go down and then it's going to go up like this. The inverse response part is due to the right half plane zero of this transfer function. Let's try to understand this physically. Here we have a reactor. This reactor has a feed and an outlet. There is an exothermic reaction taking place here. A plus other stuff gives product B plus other stuff. So this is the flow rate. When the flow rate increases, that means we dump more reactant to their system. But which is hotter or colder? Which is colder, the feed or the reactor liquid? Well, this is an exothermic reaction. So the temperature here and the temperature at the inlet are related how? If the reaction here is exothermic, that means the temperature here is higher than the temperature here, right? The feed is cold. So all of a sudden, we dump cold feed to the reactor, which is why this goes down. But by dumping more feed to the reactor, we add more reactant. Therefore, more reactant means more reaction rate. The reaction rate is is, well, concentration goes up, reaction rate goes up. Okay, which means the temperature will go up and eventually it goes up like this. Okay? It's a typical inverse response system. So the poles, the zeros of the individual transfer functions say something about the individual effect of each input variable on the output variables. The poles of the system tell us what happens with regard to stability of the system. So is this system stable around that steady state? Yes, because all four denominators have roots in the left half plane, correct? Why do they have roots in the left half plane? Say it again. So let's look at one of them. This quadratic polynomial has roots in the left half plane because all the same sign, yes. All three coefficients have the same sign. Remember the Routh-Hurwitz criterion? The Routh-Hurwitz criterion gives us necessary and sufficient conditions for the roots of any polynomial to be in the left half plane. And necessary is that all coefficients same sign. And actually there are a few more properties, a few more formulas, simple formulas that make this necessary and sufficient. But for quadratic polynomial, this is necessary and sufficient that all the coefficients must have the same sign. So if all three coefficients have the same sign, both roots are in the left half of the complex plane, whether real or complex, doesn't matter. Okay, so all three are positive, good. This is a nice stable system. The individual poles are stable, the individual transfer functions are stable, the individual zeros are okay. What about the zeros of the transfer matrix now? Zeros of G of S. Zeros of G of S are actually defined, as we said, as the point where the determinant of G of S becomes equal to 0. The determinant of this G of S is actually calculated to be, I'll have to copy it again because it's a calculation that requires perhaps a computer to do that cleanly. So if this is my G of S, the determinant of G of S is given by this. Take it up into playboard. Okay, now it copied. It copied more stuff, that's okay. So forget about this. It's screwed up. Let's try again. So if you do the calculations, you eventually get this determinant, and notice that there is pole zero cancellation here if you factorize this numerator and the denominator. So this is the determinant. At what values of S does this determinant become equal to 0? None, yes. You look puzzled, and indeed, there are no zeros. So why on earth do people look at the determinant of this transfer function to determine the zeros? Because think about IMC, we're going to do this next time. IMC inverts, for a single inverse, just inverts the plan. we want to do the same for multivariable plants. So if we want to look at the inverse of G of S, well, it's the same story again. It's the adjugate of G of S over the determinant of G of S. So for good control, if you apply the IMC method, you will want this to be stable. If it's not stable, you have to do something and you find the closest approximation. Well, to check whether this is stable, what do? Well, you look at this, right? So you look at this equal to 0, which gives you poles of G inverse, which are zeros of G of S, matrix. Okay, that's the idea. And that's what example 2 in the note gives. Example 3 is just another algebraic equation, matrix rather, algebraic exercise, which shows you a similar situation for another example, which is also interesting. It's worth sharing. So we can close with this. In this example, you have similar situation. Here we had no zeros for G of S, even though individually we do have zeros. We have zeros individually. We have a 0 here and have a 0 here individually. For the matrix, we do not. Same thing here now. It's the reverse, where you have a discrepancy. Here you have this transfer function. You have a matrix rather. You have individual zeros at 1, at 5, you do the determinant, boom, boom, boom. The 0 is in the left half plane, even though the individual zeros are in the right half. Right, so the two, this is example 3, so the two cases shouldn't be confused. The individual zeros are one thing, transfer function zeros are another, and the two, there's not even a suggestion of how these are easily related. Okay. So with that, I'll just mention that example 4, which I'm going to leave as a homework problem not to hand in, is also a worked example which shows you the same approach, the exact same procedure applied to a system that is from the biochemical field. So you see here this biochemical reactor, it's called a chemostat. Essentially, it's a vessel where cells eat stuff and produce useful stuff. Okay, so you do here a mass balance on the cells and the food that you feed them. D is what biologists call the dilution rate, which is V over F, or rather F over V, I'm sorry. It's the inverse of the residence time in the reactor. And you do the same story. You define the state equations, the output equation, which is algebraic, the product of an input and a state. You define a steady state. Actually, you define the steady state equations, and it turns out there are two of those steady states, one and another. The first one is not terribly exciting, so we go with the second steady state. The first one is when nothing happens, basically. That's also a steady state. But the more interesting is this, when you produce something. So you define the steady state, you linearize approximately around the steady state, you find the corresponding matrix A, B, C, D, and you move on to apply the eigenvalue analysis. You find the eigenvalues, you find that this is an unstable system around that steady state. You find the corresponding transfer matrix. It has two transfer functions which capture the effect of the dilution rate in the feed substrate. Substrate is food, essentially. It's another name for food to the cells. And you find this, and you can do this exercise again for this steady state. Remember, we have two steady states. There is another one which is stable. You can find the corresponding steady state. You can do simulations on Simulink, and you can also do simulations where you have the approximately linearized system, and the true nonlinear system. You see that for one variable, for one output, x times d, in this case, there is a discrepancy. In the second case, there is not much of the discrepancy for the corresponding equations solved. Linearized and nonlinear are about the same. Here, linearized and nonlinear have significant discrepancy. Is this detrimental for control purposes? Maybe it is, maybe it isn't. This is more for a more advanced course that looks directly to nonlinear systems. Our analysis will remain true, valid for linear systems, but we'll do some robustness analysis, which says I can tolerate some discrepancies between model and process, and we'll see all that in the coming lectures. With that, I'll stop here, and next time we're going to go to see how we can design controllers for multivariable systems. So I'll stop here and continue on Wednesday.